In our everyday life, we grapple with decisions all the time. Whether it's as small as do I make myself tea or coffee this morning, or as big as should I buy that new furniture for the house, once we answer the first question, we think of the next step, like do I shop for it online or offline? Each decision we make leads us closer to our final pick.
This is exactly how a decision tree classifier works. A decision tree classifier is a supervised machine learning algorithm used for classification tests. In simple terms, the model is trained on data that already has correct answers to learn how to assign inputs to specific categories. It does so by employing a tree-like structure, which we can visualize with our previous example. Let's say we decided to shop online. The first question then would be, is the product even available online? If yes, do we really need it right now? Each question we ask leads us to our final decision. Now, we can clearly see this resembles a tree. And just like a tree, the DT starts at the root node, which is the first node that best splits the data. It branches into decision nodes, which ask a question or apply a condition on features, and ends on leaf nodes where no further splits are possible. The preceding nodes are called parent nodes, and the ones that follow are child nodes. Now, that was a pretty simple diagram, but in reality, our datasets rarely look like that. Real world data is often more complex and clustered together, and the DT algorithm has to split it again and again. Now, if you look carefully, you will notice that there is a blue dot among all the reds under the horizontal line. This is known as impurity in the dataset. And DT splits the data by trying to reduce this very impurity in two ways. The first, Gini impurity, is a measure of the probability of a node element being incorrectly classified. A GI of 0 means the node is perfectly pure. Similarly, entropy measures the amount of randomness, and a 0 would mean a pure node. However, there is a trade-off here. So if we let our decision trees grow to their full length, the leaf node would end up pure. However, that would just mean that our model has memorized random noise instead of learning useful patterns, which is known as overfitting. We try to avoid this through a process called pruning, which we will notice in our later processes. Now let's take a look at our actual car evaluation data set. It's a multivariate data set with 6 categorical features and 1.7K records. The features include buying price, maintenance price, number of doors, etc. And we're trying to evaluate whether the car is acceptable, unacceptable, good, or very good. Early on, I noticed that there are no duplicates or missing values in the dataset, so not much cleaning is needed. However, there is heavy class imbalance among the targets, with 70% of the records belonging to an acceptable class. Let's jump into pre-processing. Now, theoretically, decision trees can handle categorical variables. However, implementations like scikit-learn require numerical data. So we encoded the features using ordinal encoder to preserve the national ranking and just use label encoder on the targets. An 80-20 split was done for test and training data sets with Y stratification to preserve class proportions. And finally, the model was fit to our classifier with maximum depth specified. Now, this is the type of pre-pruning done to balance overfitting. Finally, our decision tree looks like this, and the confusion matrix like this, with the correct predictions along the diagonal and an accuracy of 94%. RC curve also looks good, with the lowest accuracy still being pretty high at 87%. Now, at this point, an important question to ask ourselves is this model even better than just guessing at random? And the answer is yes, because I ran a dummy classifier on the data set, which gave a baseline accuracy of 69%, much lower than the model accuracy. A point to note here is that this should have been around 25%, given that we have 4 target classes. However, due to heavy class imbalance and this attribute, even by just guessing the most common class, the dummy classifier was accurate 69% of the times. But it's still lower than our model, so that's good. Next, I ran the K-fold cross-validation to check how well the model generalizes, and naturally it gave a lower accuracy, but still really good at 93%. At this point, I tried something interesting. I manually isolated a path from the original tree and created a new variable of miser owners by combining the lowest buying and maintenance prices. Ran the model again, and sadly, no improvement was seen in accuracy. Still a fun exercise. Lastly, I did some hyperparameter tuning. So in the original model, when we set the max depth at will, that was pre-pruning. This time I did some post-pruning using GridSearchCV to find the best max depth, which was 12. And using that, the test accuracy came out to be the highest till now at 97%. That was all from me. I hope you enjoyed the video.